Okay, so let's think a little bit about how do we talk about cache performance. And this is something that you will be expected to do. What we're going to do is we're going to run we'll give you a program and say how well, what's the hit rate of this program running on that cache? Two-way set associative, 512 lines, LRU replacement strategy. And you sort of go, whoa, that's a lot to ask, Chris. How do I figure this out? And the way you do it is, first of all, you should probably start by figuring out the sequence of addresses that will be accessed. So almost always we give you little loops, right? So this tends to be a repeating sequence of addresses. And we actually turn, this is what we call a reference string. We don't really care about the program. From the cache's point of view, it knows nothing about the semantics of the program. It just knows about the sequence of addresses the CPU is asking for. And then we basically turn those from byte addresses back into word addresses. And those we map into which cache line. And so what we're trying to do in the end is figure out what's the sequence of cache lines being accessed by the program. And from that we can determine the hit rates and things like that. So for example, here is a very simple program that is a little instruction loop, goes 100, 101, 102, 100, 101, 102. So those are the program accesses. And then it's accessing data. So it's accessing data at 1,000, and the next time through the loop it accesses at 1,001. These are word addresses. Now in a fully associative cache, how do we do the mapping to cache line? What portion of the address are we using to select where to look in the cache? This is a trick question. Yeah, so fully associative cache, we actually are going to look everywhere in the cache, right? So remember when I said a fully associative cache, t as in 2 to the t was 0, right? So in some sense, where a thing lives in the fully associative cache is completely determined at the moment I brought it into the cache. What was the least recently used location? That's the cache line it's going to live in. So the cache line that you live in a fully associated cache is unrelated to the address, right? It only related to the history of the previous accesses, right? And what we can see here, just to say a little bit more about, so we always have this notion of compulsory misses. Those are the first time you access a location, of course it's not going to be in the cache. We haven't fetched it yet. Okay, so usually at the beginning of a program, there's a certain number of compulsory misses. Typically, we're not interested in that in the performance of the cache, the steady state behavior. In theory, the loop will happen so many times that the fact that we missed everything in the first time of the loop won't matter. But what we discover is that as we bring in the data words one by one, notice that they replace each other in the cache. Right? The program, at the moment that we're bringing in a data word, okay, it turns out that the 3 instructions in the loop were always the most recently used items. The thing that's least recently used is the previous data word. Sort of makes sense, right? We're going through, and at some point in this 3 instruction loop, we're fetching some data, and it turns out the least recently used item in the cache at that point was the data fetched from the previous time in the loop, because we've touched all the other instructions since then. Right, so those, we can see that in this case, we sort of have a series of compulsory misses. So we actually have about a 25% miss rate, or a 75% hit rate in the fully associative cache. In the direct map cache, you can see we do much worse than that, right? For a while, the data addresses and the instruction addresses are mapping to the same cache line, which causes them to throw each other out. Right? So we see a lot more misses early on. Once we get to the point where the addresses, okay, are not colliding so badly with the instructions, we do a little bit better. Okay? But this one has about a 50% hit rate, or miss rate, being sort of what you'd expect. Okay, so does that sort of make sense? So here's an example of a direct map cache where some of the data accesses are colliding with some of the instruction accesses, and so what happens is that the data replaces an instruction we're going to want later in the cache. So LRU isn't saving our bacon here. It's being, the LRU effect is sort of well, we don't have a replacement strategy, I'm sorry, in a direct map cache. Now we go to an n-way set associative cache. Here's a fully associative cache. Here's a 2-way 8-line total, so 4 cache lines in each of the 2 sub-caches. and we do the same sort of program, we discover that in fact that the two-way cache is doing quite well. And in fact, it performs exactly the same, okay, as before. Now, why does the two-way cache perform, why would you expect the two-way cache to perform well? This is sort of the essence of why n-way set associative is a good idea. What do you think? Well, why did the direct map cache perform less than well? Let's start with that question. Yeah, go ahead.
Because you have your data addresses and your instruction addresses like 1,000 and 100 are colliding, but then you have two places to put those while you're looking at is 1,000.
Right. So the answer to why direct map caches aren't performing well is always, there must be a collision problem. Right? And so now you go look to see what the collision problem is, and it's the fact that the data and the addresses are competing or colliding for the same cache lines. Okay. In this particular very simple program, how many different sort of address streams are we talking about? They're interleaved, but there's the instruction address stream and the data address stream. And those are sort of two independent streams, right? And it's the fact that they interleave and collide that causes us a problem. Right, and so it turns out with only two ways, a set associative cache, if it's possible for now two addresses to map to the same cache line, because we have now two sub-cache lines where they can both live simultaneously, we discover that the two-way associative cache with this very simple program performs exactly as well as a fully associative cache, because there's really just an instruction stream and a data stream. So if you think about n-way set associative, the question you really want to ask yourself is, how many different address streams are there? Can I break them into a small number of buckets? You know, data 1, data 2, you know, instruction. You know, am I copying from one array to another? So I'm sort of thinking about the instruction, this loop that's doing the copying, you know, array 1 and array 2. And if they can all live in the cache together, then I'm going to have a pretty good hit rate. Okay. So if we talk about the associativity and the hit rate, this is a chart that's worth looking at because it sort of gets at the essence of cache design. Right? One thing you notice is that in general, having more memory, having more cache lines is better than having fewer cache lines. See, all these guys are dropping dramatically, right? And so, so making the cache bigger is almost always better, okay, than adding ways of associativity after a certain point. So what you'll notice here is that an 8-way cache, this line that's just above the fully associative, so the best you can do is down here. So this is potential measurements of a particular benchmark. You notice that the 8-way cache performs almost as well as a fully associative cache. Does that intuitively make sense? At this point, you should all be bobbing your head sort of yes, because if you think about how most programs work, there's not that many, remember that little dot diagram? There were not that many different regions of the address space that we were accessing at any given moment. The program, the stack, a couple of the data regions, right? And so it's easy to sort of, depending on how complicated the data accesses are, you can get up to 2 or 4, I mean up to about 4 pretty easily. And the extra associativity accounts for more complicated behavior about accessing several different data structures at the same time. But after that, you can put a lot more money into the cache hardware and it won't be any better. Okay, what do you own? Most of you own I forget what it is, 4 8-way 16K line cache, something like that. That's your level 1 cache on your Intel processors. Now, your Intel processors actually have 3 levels of caches, okay, where each level of cache is about a factor of 2 slower than the previous level. And so this cache here is a multi-way cache. The bigger caches tend to be more like direct map caches. Okay, any sort of? Okay, so the goal is to make a processor where what you're doing is getting the miss rate down. What do we want the miss rate to be? Well, we'd like it to be 0. We're never going to quite get there. But remember the arithmetic about computing in the average access time? Right? We figure, miss rates in the 5% range, we're looking okay. That would, if I had a 4 nanosecond cache and a 40 nanosecond main memory, a factor of 10, I could get something that had a 5 nanosecond access time if I had a hit rate of 95% or a miss rate of only 5%. So we sort of want to be down in this region of the cache. And if we're not, we start really seeing the slowness of main memory. Now, it's always possible when we're dealing with replacement strategies, you can say, well, is LRU always better? So I'm here to warn you that the word always in the question about caches is almost never true. In other words, a cache can be better. For example, a direct map cache, a bigger direct map cache is always better than a smaller direct map cache. It holds the same information. It's better. But typically when you have two-way versus direct map, FIFO versus LRU, you can always come up with a program that shows one to be better than the other. So if you see a quiz question that uses the word always, approach that with caution. You have to really convince yourself that if this cache are exactly the same except one is bigger, I mean literally bigger, it has more cache lines, but the architecture is the same, then you can safely use always. Other than that, you almost certainly can write a program to distinguish between the performances. And so, for example, this little example is using an LRU versus a FIFO replacement strategy. What we're doing is look at this sequence of addresses, and what we're trying to do is to come up with a sequence of addresses that put different items into the two different caches. So when you go home and think about this later, is this sequence of 4 addresses in an LRU cache after the 4th access, this is what's in the cache, and after the FIFO, in a FIFO cache, those are the 2 locations in the cache. And now I can make whichever one of these I want to win simply by asking for the location that the other one doesn't have. You sort of get the strategy for sort of proving caches not as good as another. So what I'm trying to point out here is more make the observation that there is no one winning strategy except usually size. If you don't change the architecture but make it bigger, typically it performs better. Other than that, I can always find ways in which one thing performs better than the other.